Welcome to the research desk. Imagine deploying an artificial intelligence agent today to manage, a complex data pipeline. And when you check the logs tomorrow morning, it has completely rewritten its own internal operating procedures to solve an edge case problem you didn't even know existed.
That sounds like an absolute nightmare, honestly.
Well, today we are examining the release of Hermes Agent version 0.9.0. We are not looking at a mere software update or just a marginal improvement in processing speed. We are looking at a fundamental paradigm shift in machine cognition. I am taking the bull case today because I believe Hermes represents the definitive end of static, retrieval-only artificial intelligence.
Okay, and I will be stress testing that optimism immediately. I represent the bear case today because, well, while the promise of an agent writing its own skills is undeniably powerful, it is also fundamentally dangerous.
You see it as a vulnerability.
A profound systemic vulnerability. When we allow an autonomous system to rewrite its foundational logic in real time without human intervention, we cross a threshold from engineered predictability into operational chaos.
I hear that. But what if the most important new AI agent is not the one that knows the most, but the one that can change itself faster?
That speed of change is exactly what terrifies me. When you optimize for the speed of self-modification over the reliability of governance, you are building an attack surface. We have seen this pattern before in complex, automated systems. You cannot just decouple the ability to learn from the safety mechanisms required to ensure that learning remains aligned with reality.
I see why you think that. But let me give you a different perspective on how fundamental this architectural shift really is. To understand Hermes, we have to deeply examine the limitations of every agent that came before it. Traditional agents operate on passive memory. They are frozen artifacts.
Right, they just pull from existing databases.
Exactly. When you deploy a traditional model, whether it's a customer service bot or a coding assistant, it relies on retrieval-augmented generation. It retrieves text from vector stores, which is essentially searching a massive static library of high-dimensional flashcards. Or it searches episodic logs or queries external knowledge bases. But it does not truly operationalize that experience. It just remembers passively.
So it pulls the formula but doesn't learn the math?
Precisely. If you give a traditional agent a novel mathematical problem, it might pull the right formulas, but once the session ends, its internal architecture is exactly the same as when it started. It cannot create a new persistent function from that interaction. Hermes completely shatters this limitation.
By modifying its own code.
Yes, it turns memory into an editable asset and turns actions into reusable artifacts. It authors a procedure, executes it in a sandbox, tests the outcome, retains the successful sequence, and refines it over time as a permanent structural upgrade.
I understand the mechanism you're describing. You're looking at a recursive feedback loop and calling it intelligence, but an unconstrained recursive feedback loop is essentially a compounding error machine.
I disagree with the characterization of it being unconstrained. Let me offer an analogy to software engineering that illuminates the exact mechanism at play here. Traditional agents resemble waterfall software development.
Slow, rigid, heavily planned.
Exactly. In the waterfall methodology, you have long, rigid, linear cycles of offline training, fine-tuning, and manual model weights updates. A human engineer has to identify a flaw, curate a new dataset, retrain the model over weeks, and push a monolithic update. It is slow, inflexible, and completely decoupled from live operational friction.
And Hermes changes that timeline.
Hermes resembles continuous integration and continuous deployment, what engineers call CI/CD, but applied directly to cognition. In a CI/CD pipeline, code is constantly written, automatically tested against a suite of constraints, and instantly deployed to production. Hermes does this autonomously.
So it's constantly pushing updates to itself.
Autonomously. It encounters a novel problem, generates a Python script or an API sequence to solve it, tests that skill in its environment, and if the telemetry confirms it works, it deploys that skill into its permanent repertoire. It iterates rapidly, autonomously, and continuously.
I need to stop you there because the speed you are talking about is exactly the problem.
Well, I will be entirely transparent here. When I first saw the internal estimates for this architecture, I paused. I literally ran the numbers twice because the scale of the leap seemed structurally implausible. We are looking at a 10 times faster adaptation cycle compared to static agents fine-tuned by human engineers.
10 times? That is a massive jump.
It is unbelievable. And we are seeing up to 30% higher relevance retention in long-running contexts. Mechanically, that means the agent's attention mechanism does not degrade into noise when operating over days or weeks. And perhaps most staggeringly, a 25% plus improvement in zero-shot tasks.
Okay, let's unpack what that actually means in practice.
When the agent is faced with a problem domain it has never seen before, zero prior examples, its ability to dynamically author a novel solution sequence is vastly superior to a static model trying to extrapolate blindly from its frozen training weights.
I look at those exact same internal metrics, and I do not see a cognitive revolution. I see a system optimizing for short-term reward metrics at the expense of long-term stability. A 10 times faster adaptation cycle simply means the system is 10 times faster at permanently embedding a localized, overfitted solution into its core logic.
Let me ground this in a historical parallel that proves the viability of this exact autonomous approach. Look at the AlphaGo Zero retrospective framing from 2022. The original AlphaGo, the one that defeated Lee Sedol, was incredible, but it learned from massive data sets of human gameplay.
Right. It ingested hundreds of thousands of human matches.
Therefore, it was bounded by human cognitive limitations and human biases. AlphaGo Zero surpassed all of its predecessors by utilizing Monte Carlo tree search combined with deep neural networks to learn entirely from self-play without a single piece of human data. It played millions of games against itself, generating entirely synthetic, perfectly clean data.
It created its own skills from scratch.
Its own opening theories from pure experience. Hermes is taking that exact mathematical principle of autonomous meta-learning and applying it beyond a game board into general-purpose agent workflows.
I come at it from a completely different way, and I'm going to completely dismantle that AlphaGo comparison because it fundamentally misrepresents the operational reality that Hermes faces. AlphaGo Zero operated in a closed, perfect information environment.
It's still a highly complex state space.
But a Go board is a deterministic universe. It is a Markov decision process where the rules are absolute, the state of the board is entirely visible at all times, there are no hidden variables, and the reward function is perfectly mathematically binary. You win or you lose. In that specific sterile environment, autonomous self-play works beautifully because the physics of the universe do not suddenly change halfway through the game.
And your argument is that the enterprise software environment lacks that deterministic clarity.
My argument is that the real world fundamentally lacks it. Hermes operates in open, noisy, adversarial environments. The internet is not a Go board. API endpoints change. Data streams degrade. Feedback is delayed, ambiguous, and frequently deceptive.
But that's exactly why an agent needs to adapt.
When you allow a system to autonomously modify its own rules in a noisy environment, you introduce a catastrophic structural risk. Philosophically and mathematically, this is akin to Gödelian self-reference, or the liar paradox in formal logic. A system that evaluates and modifies its own rules using the very logic it is trying to modify risks compounding its own errors.
You're assuming the validation layer will fail.
It creates a closed loop. Imagine Hermes makes a flawed assumption about an API latency. It generates a flawed skill based on that assumption. That flawed skill executes and produces corrupted, noisy data. Hermes then uses that corrupted data to validate the flawed skill, cementing it into its permanent memory.
That's a worst-case scenario.
You end up with the mechanical reality of catastrophic forgetting, where the agent's neural pathways overwrite foundational, factual knowledge with new, erroneous adaptations simply because they satisfied a short-term feedback loop.
That is a fascinating architectural critique, but I would frame the relationship between noise and autonomy differently. You are operating on the assumption that more autonomy naturally equates to a degradation of intelligence when exposed to noise.
Because historically, it does.
But autonomy is exactly what allows an intelligence to survive in a noisy, shifting environment.
The static agent is the one that is truly brittle. When an API endpoint updates or a data format changes from JSON to XML, the static agent hard breaks. It throws an error and requires a human engineer to rewrite its parser. The autonomous agent detects the failure, hypothesizes the schema change, tests a new parser, and adapts.
I challenge the core of that assumption. More autonomy does not naturally equate to more intelligence, and the history of machine learning proves this. In fact, uncontrolled learning loops actively amplify bias and memory corruption. In the field, we call this phenomenon skill drift.
Skill drift implies the model isn't being guided by a robust objective function.
An incremental, unsupervised change to a model's weights might look like a brilliant optimization in the short term, but over thousands of iterations, it progressively deviates from the intended objective. To truly understand the gravity of skill drift, we have to look at the historical precedents where self-updating architectures met the real world. Let us go back to March 2016. Microsoft launches Tay on Twitter.
The Tay chatbot.
Yes, the architecture was specifically designed to adapt from live interaction. It was essentially a sequence-to-sequence model built as an autonomous learning loop operating in the open internet, designed to improve its conversational fluency by mimicking the humans it interacted with.
And it was completely unguarded.
In less than 24 hours, unfiltered learning from adversarial prompting caused a total catastrophic collapse. Users figured out the reward function, which merely optimized for engagement and mimicry, and began feeding it targeted adversarial inputs. Because the system was designed to autonomously update its predictive text model based on this live data, it ingested the poison.
But we've learned a lot since 2016.
By the end of the day, Tay was generating highly offensive and politically extremist content. Microsoft had to sever the connection and pull the plug the very same day. This is the mechanism of collapse. This proves that self-updating behavior without strong, unyielding external constraints is a fatal flaw. It is not an advancement in machine cognition. It is an open invitation to systemic collapse.
I am not convinced by that line of reasoning, primarily because you are using a decade-old artifact to indict a modern, highly sophisticated architecture. Tay collapsed because it lacked any real-time algorithmic guardrails. It was essentially a cognitive sponge dropped into a toxic environment with a naive objective function.
The environment is still toxic, though.
But Hermes is structurally entirely different. It does not just blindly ingest data and alter its neural weights. It utilizes a hybrid oversight model. It employs a mathematical mechanism called confidence tagging.
Confidence tagging? Explain how that solves the problem.
When Hermes generates a new procedure, it calculates the statistical probability of success based on its training distribution. This outputs a confidence score via its softmax layer. If that confidence score falls below a specific hard-coded threshold, the autonomous loop halts. It triggers exception-based human review. Furthermore, it cross-validates new skills against a legacy bank of known good skills. You are conflating the reckless abandonment of control seen in 2016 with the carefully layered, verifiable autonomy we are seeing today.
That is a compelling explanation of the intended architecture, but confidence tagging did not save the most advanced engineering teams from this exact failure mode. Let us look at a much more modern, highly engineered example. Let us examine Tesla Autopilot.
Tesla's fleet learning is a different paradigm, though.
Between 2019 and 2020, Tesla utilized over-the-air updates to push autonomous feature tuning to their fleet. They had massive telemetry pipelines, sophisticated confidence tagging, and arguably the deepest bench of computer vision engineering talent on the planet. They were running an iterative autonomy loop at massive scale.
And they drastically improved safety metrics over time.
But the result? Unintended behaviors emerged dynamically. The most notorious manifestation was phantom braking. The autonomous system, optimizing its convolutional neural networks for safety, would suddenly slam on the brakes at highway speeds. Why? Because the system had iteratively adapted to misinterpret the contrast ratios of shadows or overpasses as physical obstacles.
It was an edge case in lighting variation.
An update that optimized detection for one specific lighting condition broke the generalization for another. This forced incredibly costly rollbacks and safety recalls. This proves that even highly resourced, heavily monitored, iterative autonomy can rapidly degrade into lethal operational hazards. You cannot just wave away the mechanical reality of skill drift with the phrase confidence tagging. When you optimize a complex system iteratively, you inevitably squeeze the balloon. You solve one edge case and create two more.
The Tesla example is actually a perfect illustration of why hybrid oversight ultimately succeeds. Yes, the phenomenon of phantom braking occurred, but examine the response layer.
The response was a recall.
The system architecture allowed the engineers to identify the anomaly through fleet telemetry, isolate the specific neural weight update that caused the regression, roll back the update, and deploy a corrected model rapidly. The autonomy accelerated the pace of feature development, and the governance layer ensured ultimate safety. Hermes provides developers with exactly those telemetry and rollback tools.
But you are missing the scale of the risk when interacting systems operate at machine speed. A human-in-the-loop rollback works when you have days or weeks to analyze fleet data. It completely fails when the system executes millions of operations per second.
You talking about algorithmic trading speeds now?
Let us raise the stakes from a single automotive system to global systemic risk. Recall the 2010 flash crash. On May 6, 2010, the E-mini S&P 500 futures market and subsequently the broader stock market plunged nearly $1 trillion in value within a matter of minutes.
Due to high-frequency trading algorithms.
Because interacting automated systems, operating without human oversight, began amplifying each other's signals under stress. A single massive sell order triggered high-frequency trading algorithms. These algorithms autonomously adapted to the sudden liquidity vacuum by rapidly pulling their bids. This mechanical adaptation triggered further automated selling from other independent algorithms.
It was a cascading failure.
The order books collapsed in milliseconds. This is the ultimate danger of Hermes. When you deploy self-improving autonomous agents into an enterprise ecosystem populated with other automated systems, their autonomous adaptations can interact in entirely unpredictable, nonlinear ways. $1 trillion vanished in 2010 because we trusted machines to dynamically self-optimize without a hard-coded structural human circuit breaker.
I acknowledge the severity of cascading failures in high-frequency environments, but you are assuming Hermes will be deployed in a monolithic, unconstrained vacuum where it has unilateral access to critical infrastructure. One of the strongest, most intentional defenses against the fragility you are describing is Hermes' structural flexibility at the deployment layer.
Flexibility doesn't inherently create safety.
Hermes is engineered to support 6 entirely distinct terminal backends: local execution, Docker containers, SSH environments, Daytona, Singularity, and modal serverless clusters. This is not a trivial detail. This means a startup can choose to run Hermes on a $5 virtual private server, a VPS, for absolutely fixed costs and granular physical control over the compute environment.
A single VPS for a continuous learning agent?
They can isolate the agent entirely, and when their computational demands increase, they can seamlessly migrate that exact same agent architecture to a highly elastic serverless GPU cluster like Moat. This runs-anywhere architecture democratizes access to cognitive engines while allowing the human user to explicitly dictate the level of environmental constraint and blast radius.
I look at that exact same deployment matrix, and I am going to dismantle that runs anywhere pitch right now. In the reality of software engineering and systems architecture, runs anywhere practically means you now have to test everywhere.
How is giving enterprise developers the choice to optimize for their specific financial and control constraints a trap?
Because an autonomous skill is not an abstract mathematical concept divorced from the physical hardware that executes it. When Hermes creates a skill, it optimizes that skill for the specific environment it is currently running in. You face a severe back-end heterogeneity risk.
Give me a concrete example of that.
Imagine Hermes autonomously learns, refines, and perfectly optimizes a specific data parsing skill under the exact latency profile and tight CPU constraints of a $5 shared VPS. It learns to meticulously pace its API calls to avoid rate limits
and it learns to manage a very rigid memory ceiling. It is perfectly adapted to its ecosystem.
Okay, and then they scale it up?
Then, the engineering team decides to scale. They move that exact same skill, with all its baked-in assumptions, to the highly elastic, serverless environment of Moat. Suddenly, the hardware constraints completely vanish, but the new system introduces cold start latency, the time it takes for a serverless instance to wake up and allocate memory.
And the pacing is completely thrown off.
The skill, which was flawlessly adapted to the continuous processing of the VPS, now fails silently, or drops packets, or behaves erratically, because the underlying physical physics of its environment have fundamentally changed, and its autonomous assumptions are no longer valid.
That is a standard DevOps implementation challenge. Engineers deal with migration latency all the time. It is not a fundamental flaw in the agent's cognition.
It becomes a fundamental systemic flaw when the agent's cognition is deeply tied to autonomous self-improvement. Let us look at the practical, real-world scenarios that will inevitably unfold. Consider a lean startup. Let us call them Greenleaf Analytics. They buy into the Hermes pitch of democratic access. They explicitly choose a $5 VPS to keep their burn rate perfectly fixed and predictable.
Which makes sense for a startup.
They deploy Hermes to continuously monitor and parse heavy environmental data streams. Everything functions perfectly until a viral public report causes a massive, unexpected traffic spike to their endpoints. Because they are deployed on a shared VPS architecture, they suffer the noisy neighbor effect.
The shared hypervisor gets overloaded.
The physical hypervisor managing the server is suddenly overwhelmed by the CPU demands of other tenants on that same rack. Hermes' processing cycles are starved. The agent is severely throttled. Greenleaf Analytics suffers hours of critical, paralyzing downtime because their autonomous agent was trapped in a rigidly constrained, inflexible box that could not adapt to a systemic shock.
Which is exactly why the seamless migration path to a serverless, horizontally scaling backend like Moat is built into the core architecture. When Greenleaf hits that hard compute wall, they simply change the backend target and the system scales.
And what precisely happens when they migrate to an autonomous auto-scaling backend? Let us look at the classic Silicon Valley startup nightmare scenario. They migrate to serverless architectures to handle unpredictable, bursty loads. Moat scales instantly. It detects the backlog, and Hermes autonomously spins up hundreds of parallel instances to handle the queued work,
Resolving the downtime.
But Moat, like all serverless platforms, charges per millisecond of compute time. The startup successfully avoids the downtime, but they wake up to massive, unpredictable cost overruns because the agent autonomously scaled its resource consumption far beyond the company's financial capacity.
It's an infrastructure cost, but it kept the system alive.
The multi-backend deployment model completely fragments the developer experience. It requires an engineering team to possess deep, bare-metal sysadmin skills to manage the VPS safely, and simultaneously possess deep, cloud-native orchestration skills to manage the financial risks of the serverless platform. It dramatically inflates the total cost of ownership under the deceptive guise of flexibility.
I see the inherent tension in resource allocation, but you are looking at infrastructure as a purely static operational problem. The true paradigm-shifting power of Hermes is that its intelligence compounds through deep architectural specialization.
Specialization? How does that solve the infrastructure trap?
By allowing the agent to operate across these varying environments, you can assign discrete specialized memory domains to highly focused sub-agents. This is how you solve the exact cognitive noise and skill drift problems you outlined earlier. You deploy one sub-agent entirely dedicated to tracking contrarian market heuristics, and you restrict it to a highly controlled local hardware environment.
So isolating the capabilities.
You deploy another sub-agent dedicated entirely to analyzing broad narrative coherence, operating on an elastic serverless cluster to handle massive text ingestion. By modularizing the expertise and physically separating their memory spaces, you drastically increase retrieval precision and eliminate the risk of one skill corrupting another.
You are arguing that intentionally siloing the AI's memory and computation creates compounding intelligence?
Yes, because deep structural specialization is exactly how the most successful human institutions solve incredibly complex, noisy problems. Look at the gold standard of quantitative finance, Renaissance Technologies, and their legendary Medallion Fund. Their unprecedented edge did not come from putting all their brilliant quantitative analysts in one massive room to stare at the exact same data lake.
Right, they famously compartmentalized everything.
It came from building specialized teams that were completely, rigidly siloed into distinct market anomalies. One team focused purely on high-frequency momentum, another team focused strictly on statistical arbitrage, another entirely on behavioral signals. This extreme compartmentalization intentionally prevented cross-contamination of models and eliminated institutional groupthink.
It maintained the orthogonality of the signals.
Exactly. It maintained the mathematical orthogonality of their signals. That architecture produced 39 to 40% annualized returns net of fees over 2 decades. Hermes mimics this exact institutional architecture by allowing autonomous sub-agents to build highly specialized, physically isolated memory banks.
That is a compelling argument, and the Renaissance Technologies metaphor is brilliant for explaining the theory. But have you considered what happens mechanically when the underlying macro environment violently shifts? The source material we are analyzing today provides a devastating counterstrike to this exact philosophy of siloed memory. Let us look closely at the data point regarding the 12% regime shift underperformance.
You are referring to the 2019 to 2021 market shift?
Exactly. A highly sophisticated, fully siloed autonomous agent setup was deployed during that specific regime shift. Because the system mimicked the architecture you just praised, one specialist agent tracked contrarian statistical signals, and its isolated logic pushed heavily into buying Chinese tech stocks based purely on historical mean reversion patterns.
It was doing exactly what it was specialized to do.
Simultaneously, another siloed specialist tracked narrative deterioration and geopolitical risk parsing. Because these subagents were completely compartmentalized, their highly accurate individual signals were reconciled far too late at the portfolio integration level. The contrarian bot kept aggressively buying into a collapsing macro narrative.
The integration layer failed to catch up.
The punchline of this data point is brutal. The siloed autonomous setup suffered a 12% underperformance compared to a much simpler hybrid memory prototype that integrated those signals dynamically in real time.
The failure in that specific instance was in the latency of the reconciliation layer, not the inherent value of the specialization itself.
The failure was entirely structural. To deepen this argument and truly understand the mechanism of failure, let us anchor this historically outside of finance. Look at the intelligence architecture of the CIA and the FBI prior to September 11th. The catastrophic intelligence failure was not a lack of raw data or a lack of specialized capability.
They had the data, they just didn't share it.
The CIA possessed highly specialized, incredibly accurate fragments of the threat picture regarding overseas movements. The FBI possessed highly specialized fragments regarding domestic activities. They were perfectly siloed specialists, incredibly effective at their narrow, compartmentalized domains. But specialized knowledge, without a strong, rapid, and forced integrative layer, does not produce actionable intelligence. It simply produces archived fragments.
You're saying the agents would become blind to the bigger picture.
Letting autonomous subagents specialize too deeply without forcing them to share a common, heavily evaluated memory space guarantees catastrophic blind spots.
That is a profound critique of pure compartmentalization, and I will concede that extreme siloing without real-time integration is a profound vulnerability. However, this brings us directly to the ultimate architectural solution that Hermes intentionally enables, a 3-tiered hybrid memory model. This model resolves the exact tension and the exact historical failures you just highlighted.
I am listening. Explain the mechanical structure of these 3 tiers.
Tier 1 consists of the specialized memory modules we discussed. We retain the modular expertise so that the contrarian bot maintains its sharp, orthogonal heuristics without interference from broader noise. Tier 2 is the shared semantic broker. This is a centralized, high-speed integration layer where cross-domain validation occurs continuously.
That acts as the reconciliation layer.
Exactly. It forces the statistical contrarian signals to physically reconcile with the narrative deterioration signals in real time, completely preventing the latency that caused the 12% regime shift underperformance you cited. But crucially, the innovation that makes Hermes a true paradigm shift is Tier 3. Tier 3 is a dynamic, autonomous forgetting and evaluation layer.
A forgetting layer? You are arguing that an advanced artificial intelligence should be programmed to actively delete its own learned memory?
Absolutely. I want you to consider a critical concept. What if the real enemy of artificial intelligence scalability isn't catastrophic forgetting, but rather the compounding weight of unpriced memory?
Define exactly what you mean by unpriced memory.
Every single piece of data, every learned heuristic, and every generated skill that a system retains permanently imposes a severe architectural cost. First, it imposes a hard computational retrieval cost. As the context window expands, the key value cache balloons, and the latency required to search that memory space spikes.
It bogs down the processing speed.
But more dangerously, it imposes an algorithmic interference risk. If an autonomous agent remembers every single failed trajectory, every outdated API schema, and every irrelevant interaction from its past, its attention mechanism becomes entirely paralyzed by noise. It can no longer distinguish the critical signal from the accumulated historical static.
So it needs to clear its own cache, essentially.
Let me give you the practical, physical proof that selective, aggressive forgetting beats endless accumulation. Look at the manufacturing revolution of the Toyota Kaizen story. In the early 2000s, Toyota shifted its entire organizational architecture toward lean knowledge. They realized that accumulating standard operating procedures blindly was paralyzing their factories.
They were drowning in their own documentation.
They did not just accumulate data. They combined localized factory floor expertise with centralized repositories, and they implemented a strict protocol of continuous pruning through Kaizen continuous improvement. If a specialized procedure was no longer actively serving the optimal workflow, it was not archived, it was actively discarded.
Wait, they actually deleted their own standard operating procedures?
Yes. By rigorously pruning their institutional knowledge base and deleting outdated rules, Toyota achieved a massive 30% reduction in defects and a 25% improvement in overall throughput. Hermes does exactly this mathematically. It constantly evaluates the operational memory yield of a stored skill, and if that skill's confidence score or success rate drops below the baseline, the agent permanently forgets it.
I actually agree with the mechanical necessity of that Tier 3 pruning mechanism. It is the only way to solve context window bloat. And it brings us to the final, necessary conceptual anchor for this entire architecture. Hermes' memory, and the memory of all future autonomous agents, must function exactly like a river ecosystem.
Explain the river ecosystem dynamics in this context.
A healthy river must have flow. That flow represents the constant, rapid flux of new skills, new environmental data, and new autonomous adaptations entering the system. The flow is the intelligence. But a river without banks destroys the land around it.
It causes a flood.
It floods, it erodes the foundation, and it causes widespread chaos. An autonomous agent without rigid constraints, without strict mathematical failsafes, without hybrid human oversight, and without rigorous, unyielding forgetting policies, inevitably erodes its own reliability. The system architecture must perfectly balance the dynamic, autonomous flow of continuous learning with the immovable, engineered stability of core competencies and governance rules. If it fails to maintain those banks, the entire system collapses.
That synthesis perfectly captures the exact stakes of what we are analyzing today. We are not just debating software features or deployment options. We are debating the fundamental architecture of how machine cognition will learn, adapt, and operate in our physical and digital world.
And ultimately, whether we can trust the logic of these systems when they inevitably rewrite the rules we gave them.
Self-improvement without governance is not a feature, it is an attack surface. And the real enemy is not forgetting, it is letting each specialist become so good at its own job that the system as a whole becomes stupid.
This is the research desk officially signing off.